In this video, I'm planning to review some problems that will be on the fourth physics test. So on page 271, number 12, it says, a 2 kilogram mass stretches a spring 3 centimeters. How far does the spring stretch when it supports 6 kilograms? Assume the spring has not reached its elastic limit. Since Hooke's law says that the mass carried by a spring is proportional to the distance it stretches, we know that for every 2 kilograms of mass that this particular string holds, it will stretch 3 centimeters. So if we change the 2 kilogram mass to a 6 kilogram mass, we know that it will stretch 3 centimeters for every 2 kilograms in this particular mass. So we take the new mass, we divide it by the original mass, and we know that there are 3 units of 2 kilograms within this 6 kilogram mass. So we know that for every one of those units it will stretch 3 centimeters. So we'll take that 3 and multiply it by 3 centimeters. And we know that now there will be 9 centimeters of stretch on this particular spring. Now there's something new we can do with this problem that's not written in your book. Let's say that we have 2 springs that have the same spring constant. I know they don't look exactly the same because I can't draw, but both of those springs can carry a 2 kilogram mass when stretched 3 centimeters. Now if we hang them side by side, some other things come into play that we've learned in other chapters of physics. We know that if this were 2 spring scales holding this 6 kilogram mass side by side, that each one would carry half of its load. So we can assume logically that each of these springs carries half the load. So each of those springs is carrying 3 kilograms. Now, if each of those is carrying 3 kilograms, how far will each of the springs stretch? Well, we're going to do the exact same thing we did before. We'll take the load that it's carrying now, we'll divide by the previous load that we know the stretch distance for. When we do the division, we find out that it will stretch 1.5 times the amount it had stretched up here. So we'll take 1.5 and multiply by 3. And when we do the multiplication, we find out that each of these springs holding the 6 kilogram mass side by side will stretch 4.5 centimeters. Now that makes logical sense because we know that one spring holding this mass would stretch 9 centimeters and they're each holding half, so that would be 4.5 centimeters. Now let's look at page 287, number 20. When the pressure in a hydraulic press is increased by an additional 10 newtons per centimeter squared, how much extra load will the output piston support when its cross-sectional area is 50 square centimeters? Now, in order to understand this and think about it more easily, we'll draw a picture. On this side of the picture, we have 10 newtons of force being applied over 1 square centimeter. On this side of the hydraulic press, we have 50 square centimeters. Now we know that Pascal's law tells us that every molecule of water exerts the same amount of pressure in all directions. So this 10 newtons of force is going to be multiplied over here so that every centimeter squared exerts 10 newtons of force. So now we have 50 centimeters squared instead of 1 centimeter squared. And each of those 50 centimeters squared exerts 10 newtons of force because force is applied through molecules of a liquid in all directions. So we can calculate the force in the output by multiplying how many units of area are over here times the amount of force that is put into this side. And we see that 10 newtons per centimeter squared times 50 centimeters squared equals 500 newtons. The centimeters on the bottom of the fraction cancel with the centimeters on the top of the fraction. Now let's say I ask the question a little differently. Let's say we know that this hydraulic press can hold a car weighing 30,000 newtons, and the area of this hydraulic press is 50 centimeters squared. That's going to be a mighty dense car since 50 centimeters squared isn't very big, but let's just pretend. Now, this side of the hydraulic press, where the piston is, or the input force is applied, is still only 1 centimeter. So we know that there's going to be 50 times the force on this side. Now, in order to know how much needs to be put into the input, we need to know how much force is exerted over 1 square centimeter on this side, because that will tell us how much force has to be put into this 1 square centimeter over here. We're going to do that by dividing. So 600 newtons per centimeter squared need to be applied to the piston here in order to lift this car. Now, what if I changed the dimensions of this particular hydraulic press? Now the input has 10 centimeters squared and the output has 100 centimeters squared. The car still weighs 30,000 newtons. So instead of dividing by 50 centimeters, we're going to divide by 100 centimeters. Now we can see that the force that needs to be applied is 300 newtons per centimeter squared. Since 300 newtons must be applied to every centimeter squared in order to lift this car, how much total force is going to be applied over here? Well, 300 newtons for every centimeter squared. So that would be a total of 300 times 10. So a total of 3,000 newtons would have to be applied over here. Now let's talk about weight density versus mass density. We haven't called it mass density before, we've just called it plain old density. So mass density is your original density formula, which is density equals mass divided by volume. And this italicized lowercase p is the symbol for density. Now when we talk about weight density, we're taking mass density and we're applying gravity to it to give it weight. So here you can see I added a g for gravity. So weight density is mass times gravity over volume. Mass density is just mass over volume. Now it's important to know what units of measurement are used for these measurements. Whenever you see newtons, you know that newtons is equal to mass times gravity or weight. If you see kilograms, you know that kilograms is just plain old mass, and there is no weight yet applied. So you need to look carefully at questions to see whether mass is given or weight is given. And if weight is given, are they asking for mass or are they asking for weight? And look at your formula to see whether you need to apply mass or if you need to apply weight to the formula. Now let's look at page 288, number 44. A gravel barge, rectangular in shape, is 4 meters wide and 10 meters long. When loaded, it sinks 2 meters in the water. What is the weight of gravel in the barge? Now, we know that whatever the volume is that sinks into the water is going to be equal to the volume of water it displaces. And whatever the weight of the water it displaces is, will be the buoyant force that acts on it. And that buoyant force has to equal the weight that it's holding up. Otherwise, this gravel barge will sink. We're assuming that the gravel barge is not going to sink. So the weight of the gravel is going to equal the weight of the water displaced. Now, how are we going to find the weight of the water? Well, we can use a density formula for that. We know that the weight density of water is always 9,800 newtons per meters cubed. And we know partially the volume of this particular amount of water because we have two dimensions, the length and the width of the barge. We also know the depth that it sinks into the water, which will give us our third dimension, and that gives us meters cubed or volume. So we'll be solving for weight. So we can rearrange this formula to solve for weight. If we put the original formula into the triangle here, whatever's on the top of the fraction always goes in the top of the triangle. The other two go either to the left or to the right of the bottom, depending on where they are in the formula. So if we want to solve for volume, we say volume equals, we put a finger over that, and it's weight divided by weight density. If we want to solve for weight density, we can put a finger over this and say weight density equals weight divided by volume. Now if we want to solve for weight, these two are next to each other, so we know weight is equal to weight density times volume. And we know the values for these two things. When we do the multiplication, the meters cubed on the bottom is canceled out by 1, 2, 3 meters multiplied together, which is meters cubed. So we come out with 784,000 newtons, which is the weight of the water displaced. And that also has to equal the weight of the gravel in the barge because that water displaced is holding up the gravel and it's floating. Now let's look at page 289, number 49. The cross-sectional area of the output piston in a hydraulic device is 10 times the input piston's area. Let's draw a picture for that. Now if 5 newtons of force are applied here, how many newtons of force will be multiplied over here, or how much force will come out over here? Well, if every 1 centimeter squared has 5 newtons here, then every 1 centimeter squared on this side will also have 5 newtons. And since there are 10 of them, we can say 5 times 10, and there will be 50 newtons. So you can see that the output of this particular hydraulic device is 10 times the input. Now, how far will the piston move compared with the distance of the input piston is the key to understanding a hydraulic device. Because of energy conservation, the force times the distance on this side must equal the force times the distance on the other side. So if the force over here is 5 newtons and it moves 10 centimeters, And we know the force over here is 50 newtons. How many centimeters can this move? Well, 5 times 10 is 50. And 50 is already here, so it can only move 1 centimeter. This satisfies the energy conservation. Force times distance equals force times distance. 5 times 10 equals 50 times 1. Now, let's change some things. Using these numbers, I'm going to ask you, for each centimeter that the input piston moves, how much will the output piston move? Well, if it moves 1 centimeter, this side will have to move 1/10 of a centimeter. Basically, what's happening here is, if you can get this unit down to 1, this will be the reciprocal. The amount of distance this side moves will be the reciprocal of its however many times bigger it is than that. So let's try it again. Let's say this side is 1 centimeter cubed and this side is 3 times as big. If this side is moved 10 centimeters, how far is this side going to be moved? Well, we're going to use the reciprocal of the multiplication that we did on this side. So this was multiplied 3 times. And if this moves 10 centimeters, this will move 3 1/3 centimeters. Now let's ask one more question. Let's say the output piston is 5 times the input piston. And let's say we move the input piston 2.5 centimeters down. What is the distance that this side will move? So we'll take the reciprocal of 5, and you can only use the reciprocal if this side is 1, because you know it was multiplied by 5 times. If this was 2 and 10, you wouldn't use 1/10, you'd have to reduce and use 1/5. Now we see that if this side is 1 centimeter squared and this side is 5 centimeters squared, so it's 5 times larger. If we move this side down by 2.5 centimeters, this side will move up by 0.5 centimeters. Let's look at page 304, number 20, which says calculate the approximate weight of air in your classroom. So, how are we going to do that? Well, we have some measurements that we know about air. We have a standard unit of measurement for the density of air, which is 1.25 kilograms per meters cubed. And we'll assume that the classroom has the dimensions of 20 meters by 15 meters by 9 meters. Now, we have to look and see what we're asking for. Are we asking for the weight or the mass of the air? Because if we look at this density of air formula, we see that this is the mass density of air. If we want to find out the weight density of air, we're going to have to multiply by gravity. So we've added in gravity so that we now have the weight density of air, which is 12.5 newtons per meters cubed. Notice that kilograms times meters per second squared is newtons, and here's the meters cubed, so all of the units are applied. Now we're going to solve for weight from the weight density equation. So again, if we're looking for weight, which is on the top, we're going to multiply weight density of air times the volume. And we come out with the answer being 337,500 newtons of weight of air in the classroom. That's a lot of weight. Let's look at page 305, number 41. The density of liquid air at standard temperature and pressure is about 900 kilograms per meters cubed. What will be the volume of 1 meter cubed of liquid air when it turns to its gaseous form? So now, if we're going to find the volume of air in its gaseous form, we need to do a couple of things. We need to know what the mass is, and we need to know what the density is. So here we have the density of liquid air, but we've already talked about the density of gaseous air. Now this again is the mass density, not the weight density. But if you look here, we're given mass and not weight, so I'm using the appropriate equation. Now what we're looking for this time is volume. So if I put my finger over the volume, we have mass on the top and density on the bottom. Now the question is, how much mass do we have of liquid air? Well, it tells us that we have 1 cubic meter of liquid air, and it tells us that there are 900 kilograms of liquid air per each cubic meter. So we must have 900 kilograms of liquid air. Now, when the liquid air turns into a gas, are we going to lose any mass? And the answer is no, we're not going to lose any mass because the mass is not going to disappear. It's just going to spread out when it turns into its gaseous form. So we'll still have 900 kilograms of air. We're going to divide it by the density of gaseous air, which is 1.25 kilograms per meters cubed. Now when we do the math, the kilograms cancel one another out, and we're left with meters cubed, which is the appropriate units for volume, and we come out with 720 meters cubed. Now let's look at page 305, number 42. How many newtons of lift are exerted on the wings of an airplane that have a total area of 100 meters squared when the difference in air pressure below and above the wings is 5% of atmospheric pressure? Now, atmospheric pressure is a given. It's stated in the book as 100,000 newtons per meter squared, which is also called 100,000 pascals. Now, the question is asking us for lift, which is a force, and it's telling us that it's newtons of force, so we know that our answer is going to be given in newtons. One other thing the problem tells us is that the pressure difference is 5% of atmospheric pressure. So the difference in pressure is going to tell us how much lift is given to each square meter of the wing that is causing the difference in atmospheric pressure. So first let's find the difference in atmospheric pressure. We see that 5%, which is 0.05 when you're using it in multiplication, times atmospheric pressure is 5,000 newtons per meter squared. Now, the problem also tells us that the wings have a total area of 100 meters squared, and therefore we need to realize that every meter squared has 5,000 newtons of lift being applied to it. So the total lift would be 5,000 times however many meters squared there are in the area. And we see that the total lift on the wings of this airplane is 500,000 newtons. Let's look at page 679, number 1. Calculate the approximate volume of a person of mass 100 kilograms who can just barely float in fresh water. Now, if this person can just barely float in fresh water, we know that the water that is displaced by this person has to equal the weight of the person. So the weight of the water displaced by this person is going to equal the weight of the person. And since the person can just barely float, we know that the entire volume of this person, approximately, probably their nose is sticking up out of the water to breathe, is displacing the water. So we can assume that the volume of the water equals the volume of the person. Now, if we're going to find the weight of this person when we're given 100 kilograms of mass, we would have to multiply it by gravity to find its weight. So the weight of the person is 1,000 newtons. So since the weight of the person is equal to the weight of the water displaced, we can use the formula for weight density, solve for volume, and then substitute numbers. And when we divide, we find out that the volume of the person is 0.1 meters cubed. Let's look at page 679, number 5. When a 2-kilogram object is suspended in water from a spring scale, the scale's reading is 1.5 kilograms. What is the density of the object? And I'm going to add in the question, and how does this density compare with the density of water? Now, the first thing we have to realize is if this 2-kilogram object is suspended in water and the reading is only 1.5 kilograms, then the buoyant force holding that up is 0.5 kilograms. So in order to find the density of the object, we need to realize that the stone is displacing 0.5 kilograms of water. If the stone is displacing 0.5 kilograms of water, we can find out the volume of that particular stone. The volume of the water displaced turns out to be 5/10,000ths of a meter cubed. Now, we know the mass of this particular rock. So in order to find the density of the rock, we have the mass. We now have the volume of the rock, which is equal to the volume of the water displaced, and we can find the density of the rock. So when we replace the formula with numbers, the mass of the rock, 2 kilograms, divided by the volume of the rock, 5/10,000ths of a meter cubed, we come out with 4,000 kilograms per meter cubed as the density of the rock. Now, how does this compare to the density of water? It's 4 times the density of water. Now let's look at page 679, number 6. How much pressure do you experience when you balance a 5-kilogram ball on the tip of your finger? Say an area of 1 centimeter cubed. So if we were going to do this, we have to know the formula for pressure. Pressure is equal to force divided by area, and we have to realize that force is weight, or mass times gravity, not just mass. This problem has given us mass, so we have to take that mass and multiply it by gravity. 50 newtons per centimeter squared is the pressure. Now, if you wanted to change this to SI units, you would have to say 50 newtons per centimeter squared and do 1 unit multiplier for each of the centimeters that you're replacing. So centimeter squared is canceled out by centimeter times centimeter, and you'd come up with 500,000 newtons per meter squared. Now, what if the problem asked you if you were going to hold this particular ball with 4 fingers and each finger was 1 centimeter squared? Now you would have to change your dimensions. The 50 Newton ball would now be being held by 4 centimeters squared. and you would come up with 12.5 newtons per centimeter squared as the pressure that is being exerted on each finger. Then if we wanted to change it into SI units again, we'd have 125,000 newtons per meter squared. Now let's look at page 679, number 3 at the bottom. Air in a cylinder is compressed to 1/4 its original volume with no change in temperature. What happens to its pressure? This is an application of Boyle's law. The pressure times the volume of the original setup equals the pressure change times the volume change, as long as the temperature doesn't change and no mass is lost. So if in this particular cylinder, let's say the pressure was 1 and the volume was 1. We don't know what the pressure is after the volume is compressed, but we know the volume is compressed to 1/4 of its original. So now we have 1 equals pressure over 4, and in order to make that true, we know that pressure would have to equal 4. So when the volume is reduced by 1/4, the pressure goes up by 4.